Hi everybody, welcome back. In this video, we'll introduce color critical graphs. I'll show you some examples of some color critical graphs or K-critical graphs. I'll give you some motivation for why someone would want to study such objects. And lastly, I will prove a theorem, Theorem 14.13 from our text, which gives us information about the edge connectivity of a K-critical graph. Let's get started. So first off, a graph is called color critical if the chromatic number of any proper subgraph of the graph is less than the chromatic number of the graph. So what's really going on here is we're looking at graphs that are just barely K-colorable or not K-colorable, but rather that are just barely K-chromatic for some K. In the sense that if you looked at any proper subgraph, removed any edge, removed any vertex, you would end up with something, a chromatic number that's smaller. So these are sort of minimal K-color or K-chromatic graphs. So if the graph is color critical and it's also K-chromatic, we say it's critically K-chromatic or just simply K-critical. So I'll usually use this term K-critical for a graph with this property, and chromatic number of G is equal to K. So first off, a couple examples of graphs with this property. One big family of graphs with this property, well, let's take a look here at K4. So here's K4. As we know, it takes 4 colors to do this. But if I look at any proper subgraph, well, if I say removed a vertex is either 1 complete of order less than or equal to 4, rather less than or equal to 3. I either get a complete graph of order less than or equal to 3, or 2, I get a non-complete graph. Non-complete graph. And in this case, the order would be, we could say at least, or at most 4, rather. In either of these cases, so if I have the complete graph of order 3, my chromatic number of the proper subgraph would be less than or equal to 3. And same thing here, if I have a non-complete graph of order at most 4, remember if it's non-complete, I never need to use I never need to use the order of I never need to use n colors to color the graph. It's less than or equal to n minus 1. So this would also be less than or equal to 3. However, the chromatic number of G is exactly 4. And so K4 has this property. In fact, this is true for any Kn. Right? If I take Kn and I look at any proper subgraph, I'd have a complete graph of order at most n minus 1, in which case my chromatic number of any proper subgraph would be at most n minus 1. Or I'd have a non-complete graph of order at most n, in which case the chromatic number of the proper subgraph would be at most n minus 1. And so complete graphs of order n at least 2 are, we could say they are n critical graphs, right? Their chromatic number is n, and the chromatic number of any proper subgraph is at most n minus 1. So yeah, Kn of these are all n critical graphs. As another family of graphs, if we look at odd cycles, well, if I remove any vertex or any edge from an odd cycle, I end up with I eliminate the odd cycle, right? If I take, say, K5 or C5 rather, if I take, say, C5 and I look at any proper subgraph, so remove any edge, any set of edges, any set of vertices, well, we'll eliminate the odd cycle if we do anything like that, and so it'll be bipartite. Bipartite And so any proper subgraph, let's call it H, that'll have chromatic number of H will be at most 2. And so remember that odd cycles, the chromatic number of any odd cycle is exactly 3. And so this tells us that that odd cycles are 3 critical. Chromatic number 3, any proper subgraph has chromatic number less than 3. Now actually, we can say more here. Not only are all odd cycles 3 critical, but actually any 3 critical graph is also an odd cycle. So why is that the case? Well, if you take a 3 critical graph, that means its chromatic number is 3, which means it's not bipartite. So chi of G equal to 3 implies not bipartite, which means it has an odd cycle. It means it has an odd cycle. But what's more, since it's 3 critical, that means any proper subgraph has chromatic number at most 2. So chi of H less than or equal to 2 implies that any proper subgraph is bipartite. So what that means is, one, so G has to have an odd cycle. And because of this property, it means every edge lies on an odd cycle. And actually, even more, removal of any edge must eliminate the cycle. And so that means that G contains exactly one odd cycle. Every edge lies on that odd cycle. Hence, G itself, G is an odd cycle. And so we have actually both directions here. The 3 critical graphs are exactly the odd cycles. Actually, there's no known characterization for 4 critical graphs. They don't follow such a nice pattern. So why might one study K-critical graphs? Well, one, this restriction that any proper subgraph has at most the chromatic number of the original graph, well, that's a lot to work with. We'll be able to prove some theorems that give us some nice structural information about the graph, knowing that it's K-critical for some K. So we get some nice information there. And then second, every K-chromatic graph contains a K-critical subgraph. And so even if our graph's not K-critical, we can find a K-critical subgraph and gain all of this information. We'll have to, of course, modify it a little bit since we're talking about a subgraph, but we'll be able to use the information we prove about K-chromatic graphs or the information we prove about K-critical graphs to prove things about K-chromatic graphs in general. So here I just want to illustrate why every K-chromatic graph contains a K-critical subgraph. Well, the idea is if you start removing edges, removing vertices, eventually you'll get to some point where the removal of any edge or vertex lowers the chromatic number. And so what we're really saying here is, I'll say let H be a minimal, and I'll say with respect to size, a minimal K-chromatic subgraph of G with no isolated vertices. Graph G with no isolated vertices. Then, since it's minimal with respect to size over all these K-chromatic subgraphs to do without isolated vertices, what this means is that if I remove any other edge, so if I look at any proper subgraph of H, then the chromatic number must decrease. It would be at most K-1 chromatic. Then H is K-critical because it's both K-chromatic and has this property. All right, we'll see how this comes to use. All right, so here I want to point out a couple a couple things we can say about the relationship between connectivity and k-critical graphs. So remember, corollary 14.5 said that the chromatic number of a disconnected graph, so here G is disconnected, so the chromatic number of G is the max of all of the, so G is disconnected components, G sub I are the components of the graph. It's the max of the chromatic number of all of the components. Max of G sub I didn't make sense. Chromatic number, max of the chromatic numbers of the connected components. And so what that means, if I have a disconnected graph, well, I could just say remove the smallest component, for instance, and I remove that, and my chromatic number will stay the same because I haven't affected the maximum of the connected components. So that is, any disconnected graph cannot be k-critical. What that means is if G is k-critical, then G is connected. So that's just connectedness, so that's nice. And then remember theorem 14.6, which said that if G is separable, but really we don't need to say G is separable, but and B sub I are the blocks, right? The non-separable, maximal non-separable subgraphs of G. Then we have that the chromatic number of G is the maximum of the chromatic numbers. Maximum of the chromatic numbers of each of the blocks. So again, if my graph contains a cut vertex, if I have more than one block, then I can say remove the block, not the entire block, but the branch at that cut vertex. Remove that branch, and I'll have a graph with still the chromatic number of G equal to the max. And so that is, if G has a cut vertex, then it is not k-critical. And so we can say if G is k-critical, then G is 2 connected. So we can say, we can have these relations, and since it's actually 2 connected, this also implies that it's 2 edge connected. And so this big theorem in this section, one of the big theorems here, is further establishing this relationship between k-critical graphs and their edge connectivity. So what more can we say here? Well, actually, if G is k-critical, then it's k-1 edge connected. So let's kind of go through a proof sketch of this theorem. The only 2 critical graph is K2. That's pretty easy to see, and that's right. That is 1 edge connected because it is a connected graph. The 3 critical graphs, as we saw before, are the odd cycles, and odd cycles, of course, they contain no bridges, and so they are 2 edge connected. Remember, that means no bridges. And so we'll assume K is at least 4. All right, so we give ourselves, we're going to prove this by contradiction. We'll suppose we have a k-critical graph that's not k-1 edge connected. And remember back to chapter 4, what we can say if it's not k-1 edge connected. Remember, this means that there exists a set of k-2 edges whose removal disconnects the graph. And so if we take those set of k-2 edges, we can find a partition of the vertex set so that the number of edges joining V1 and V2 is at most k-2. So what we have is a picture like this one, where we have at most at most, we call this set E prime of edges, that the number of edges between V1 and V2 is at most K minus 2. What we're going to do is we're going to, let G1 be the, we'll think of V1, the graph induced by vertex set V1 as a graph, as well as G2 induced by V2. And they are both K minus 1 colorable because G is K critical, and these are proper subgraphs. So each of those is K minus 1 colorable, and we'll color each of them using the same K minus 1 colors. Now, since our graph is, again, since it's K critical, that means the original graph, the chi of G, right? G is the whole graph here. Chi of G is equal to K. And so what has to happen, if I color the vertices V1 with K minus 1 colors, the vertices V2 with the same K minus 1 colors, what I'll have to see happen in order for G to be K chromatic is I have to see, no matter what coloring I give, I have to see an edge in vertex in V1 and a vertex in V2 colored the same. That is, that if I smash these two colorings together, I don't end up with a coloring of G. For otherwise, right, if that didn't happen, that means I would have a K minus 1 coloring of G. So I have to have something like this. Now, the proof strategy here is that actually, if I have something like this, there exists a permutation of the color classes of V1 that will remove any situation like this. And hence, the original graph is K minus 1 colorable, which contradicts our choice of G to be K chromatic. So how does this work? How can we do this? Well, what we do is we look at the color classes of G1. So in that K minus 1 coloring of G1, I'm going to call these U1 through UT. These color classes, and actually these U1 through UT, these are just the color classes for which there's some vertex in UI adjacent to a vertex in V2. So that means there's some other color classes of this K minus 1 coloring of G1. They're all right here. They don't have vertices that are adjacent to vertices in V2. And so I know I will never have this situation where I have a vertex here adjacent to a vertex here of the same color. That's not going to happen with these, so I just look at the sets where this can happen. And what I'll do is I'll come up with a strategy for permuting the colors of these things that avoids a vertex here being adjacent to a vertex here of the same color. So in order to establish this, well, I look at the number of edges between each U sub I and V2. I'm going to call this K sub I, be the number of edges here. And then what I can say is, remember, E prime is the set of all of these edges. So what I can say is that the sum of the K sub i's from I equal 1 to T is at most n minus 2. And so that tells me lots of stuff, right? That tells me K1 is less than or equal to n minus 2. It tells me K1 plus K2 is less than or equal to n minus 2. And so on, right? Any finite or any partial sum of this will also be less than or equal to n minus 2. Furthermore, I know that by how I define these U sub i's, I know that K sub I is at least 1 for each I. So that'll be important. And so let's just say, for instance, that I do have in U1, I have this case where I have a vertex, let's say colored 1, that's adjacent to a vertex in V sub 2 that's also colored 1. So this would be a problem. This is what I'm trying to eliminate. I'm trying to permute my colors so this doesn't happen. So I want to avoid this happening. So that means all my colors here in U1 are colored, or all my vertices in U1 here are colored 1. And I might have some other vertices. So maybe there's a vertex here that's colored 1, that's adjacent to another vertex here that's colored 2, right? So in terms of permuting the colors, I couldn't change 1 to 2. I would still have the same issue. So the question is there a color available such that no vertex here is adjacent to a vertex in V2 of that color? And the answer is yes. So how many colors do I need to avoid? So in permuting colors to avoid a vertex in U1 adjacent to a vertex of the same color in V2, we need to avoid, let's see, so we have K minus 1 total colors. And how many do we need to avoid? We have K minus 1 minus, so at most there's K1 vertices over here that are adjacent to vertices here, right? K1 is the number of edges from U1 to V2. So that means I have K minus 1 minus K1 options. And then that's how many colors I have left over that I could use here. But of course, let's see. So if I take this and I rearrange this a little bit. Oh, sorry, this isn't n minus 2. This is k minus 2. K minus 2 less than or equal to k minus 2. So if I take this a little bit and rearrange it, I can see that k minus 1 minus k1 is at least 1. Just do some algebra and rearrange that. This is at least 1, so there is some color we can change U1 to avoid this situation where we have a color here adjacent to a color here. And we don't just change this color, right? We permute the color. So I'm going to swap this color with another one of these color classes. I'll swap it with one of those. And then we move on. So that takes care of U1. When I permute the colors, that ensures that no vertex of U1 is adjacent to a vertex in V2 of that same color. So then we move on to U2. Now things are a little bit different for U2. I want to permute the colors. We have at most K minus 2 edges coming here. We still have this property that K minus 1 minus K2 is at least 1. So there's at least one color available we can switch it to. However, we need to be a little bit careful. In permuting the colors for U2, we don't want to change the color for U1. So that is, there's another color that we have to avoid here. Right? We don't want to sort of backtrack and undo things we already did. So in permuting colors to, I'll say, fix U2, we also need to avoid the color used for U1. So that's an extra color I have to use, or I have to avoid, and so that's, I have K minus 1 total colors, and now I have to avoid not just K2 colors, but K2 plus 1 colors. Now, of course, I have K1 plus K2 is it less than or equal to K minus 2, and I know K1 is at least 1, and so this is greater than or equal to K minus 1 minus K2 plus K1, and since I know any partial sum of this is less than or equal to K minus 2, I have at least one color here for this. So I still have one color. And so I can permute the colors of U2 while leaving the colors of U1 fixed, and fix U2 so that there's no vertex here adjacent to a vertex here of the same color. Now, hopefully you can generalize this now. I can keep doing the same process. I'll keep having more colors that I need to avoid, but since any partial sum of this is at most K minus 2, I'll be able to follow the same logic that I did here and see that we always have at least one color available to permute. And in any case, I can fix that color class and end up with a coloring so that no two vertices that share the same color are adjacent. Hence, G is K minus 1 colorable, which is a contradiction because we assumed G was K critical and hence K chromatic. And so that proves this result. All right, that's the idea there. So a couple consequences of this result. remember that the edge connectivity of the graph is the greatest value of k for which g is k edge connected. That means if g is, let's say, chi of g critical, then by the last theorem, it's chi of g minus 1 edge connected. And the edge connectivity is at least that. So the edge connectivity lambda of g is at least chi of g minus 1. And so this tells me that this gives me an upper bound. Chi of g is at most the edge connectivity of g plus 1. So there's a nice upper bound for the chromatic number of a graph. And that's so that's only for critical graphs do we have this property. This won't be true for any graph. However, since every graph contains a k-critical, every k-chromatic graph contains a k-critical subgraph, that means that if we look at all the subgraphs, we take the maximum. Well, certainly the chromatic number of a k-critical subgraph is less than or equal to this maximum, and so that proves this result. We can look over all the subgraphs. Now, this is sort of a hard thing to compute. However, it will be theoretically, it'll be helpful for us in a future video here. And then as well, so if we have a color critical graph, we have that property of edge connectivity. And then if you remember that the edge connectivity of a graph can never exceed the minimum degree of a graph, we get this result for color critical graphs. And hence, since every graph contains a k-critical subgraph, we can look over all the subgraphs and take the maximum, and that'll give us a bound. So one note here is you might be wondering about vertex connectivity. So here's an example of a 4-critical graph. So certainly the chromatic number of g is 4. It does take 4 colors to do this. Yet if you inspect all of the proper subgraphs here, you'll see that it's k-critical. So this is a 4-critical graph. However, it's not 3 vertex connected. It's not 3 connected. I can say remove these 2 vertices and end up with a disconnected graph. And so while we can say this result about edge connectivity, the same is not true for vertex connectivity. Okay, that's it for this video. In the next video, we'll look at some more bounds on the chromatic number. I'll see you there.